What specific problem does the Avat3r method aim to solve in the context of creating 3D head avatars from casual images?
The Avat3r method aims to solve the problem of reconstructing animatable 3D head avatars from just a few casual images, which is challenging due to several factors. These include the under-constrained nature of sparse 3D reconstruction, the need for plausible facial animation without prior examples of the person speaking, and the inconsistencies in input images caused by the subject's movement during capture. Unlike existing methods that require extensive data or focus on frontal views, Avat3r leverages a novel architecture that predicts 3D Gaussian representations for each pixel, allowing it to generalize over facial expressions while conditioning on the individual's identity. This approach simplifies the task by avoiding the need for a fixed template mesh and enables the creation of high-quality avatars quickly and efficiently, making it suitable for casual use cases.
Can you provide a detailed explanation of how the Avat3r method works? Please illustrate it step by step, focusing on each component and their interactions within the pipeline.
The Avat3r method operates through a multi-step pipeline designed to create high-quality 3D head avatars from just a few input images. First, it utilizes two pre-trained foundation models, Avat3r, which generates dense position maps for the input images, and Sapiens, which extracts rich low-resolution feature maps. These position maps help in placing 3D Gaussians accurately, while the feature maps assist in view matching. Next, the core of Avat3r employs a vision transformer architecture that processes the input images along with the position and feature maps. It begins by patchifying these inputs and applying self-attention layers to infer 3D information. To enable facial animation, cross-attention layers are introduced, allowing image tokens to interact with a sequence of expression tokens derived from a descriptive expression code. After processing, the model upsamples the output to the original resolution and incorporates skip connections for positions and colors, ensuring that the generated 3D Gaussians accurately reflect the pixel's geometry. Finally, a confidence mask derived from Avat3r's confidence maps determines which pixels will spawn 3D Gaussians, allowing for a dynamic adjustment based on the individual's features, such as hair volume. The final 3D representation can then be rendered from any viewpoint using a differentiable rasterizer, completing the avatar creation process.
Can you walk through a simple example of how Avat3r processes input images to produce a 3D head avatar? What are the important stages in this example?
Avat3r processes input images through a series of well-defined stages to produce a 3D head avatar. First, it takes a set of 4 input images, which can be captured at different times or from various angles, along with their corresponding camera parameters. The model then utilizes Avat3r to generate dense position maps for these images, which help in aligning the 3D Gaussian representations. Next, the Sapiens backbone extracts rich feature maps from the input images, enhancing the model's ability to match views and produce sharper predictions. Following this, a vision transformer architecture processes the combined information from the input images and their features, applying self-attention and cross-attention mechanisms to infer 3D information and animate the head according to a specified expression code. Finally, the model generates a set of 3D Gaussians, which are rendered from any desired viewpoint, resulting in a high-quality 3D head avatar.
What theoretical or practical benefits does Avat3r offer when compared to existing methods for creating 3D head avatars?
Avat3r offers significant theoretical and practical benefits over existing methods for creating 3D head avatars, primarily by enabling the reconstruction of high-quality, animatable 3D avatars from just a few images, as opposed to the hour-long sessions and expensive setups required by traditional methods. It effectively addresses the challenges of sparse 3D reconstruction, face animation, and robust reconstruction simultaneously, which existing methods struggle with due to their reliance on extensive input data. Avat3r's architecture utilizes a vision transformer and incorporates position maps from Avat3r, allowing it to maintain geometric fidelity even with inconsistent input images, a common issue in casual settings. Additionally, it avoids the need for expensive test time optimization and can generate avatars in a matter of minutes, making it more accessible for casual users. Finally, Avat3r demonstrates superior performance in metrics such as PSNR, SSIM, and identity similarity, indicating that it produces more realistic and temporally consistent avatars compared to state-of-the-art systems like GPAvatar and GAGAvatar.
How did the authors validate the effectiveness of the Avat3r method? What metrics and experimental design were used to test its performance?
The authors validated the effectiveness of the Avat3r method by conducting quantitative comparisons against recent state-of-the-art systems, specifically GPAvatar and GAGAvatar, using the Ava256 dataset. They evaluated the ability to create realistic 3D head avatars from just 4 input images, measuring performance using metrics such as peak signal-to-noise ratio, PSNR, structural similarity index, SSIM, learned perceptual image patch similarity, LPIPS, and the perceptual video metric JOD for visual similarity in rendered videos. The experimental design involved training GPAvatar under the same conditions as Avat3r and rendering videos of 100 frames from the frontal camera for each holdout person to assess alignment, temporal consistency, and identity similarity. Additionally, they tested Avat3r's generalization capabilities on the Ensemble dataset, which had different lighting and camera parameters, further demonstrating its robustness. The results indicated that Avat3r outperformed the baselines in key metrics, producing more expressive avatars with higher rendering quality.
What are some limitations or drawbacks of the Avat3r approach, particularly in terms of its requirements or the quality of the generated avatars?
The Avat3r approach has several limitations, particularly regarding its reliance on a 3D GAN for lifting single images to 3D, which can introduce errors and lead to a loss of detail in the final avatar. Additionally, the method requires accurate camera pose estimates during inference. Incorrect estimates can result in errors, which may affect the quality of the generated avatars. Furthermore, Avat3r does not provide control over lighting, as it bakes in lighting effects from the input images, potentially making the avatars appear out of place in novel environments. Lastly, while the model can create avatars from a few images, the quality may still be hampered by the limitations of the 3D GANs used, especially those that rely on screen space super resolution, which can introduce view inconsistencies.